I welcome all of you once again in the session. Today I will discuss the electrospinning of lead-free ceramic nanofibers for energy harvesting application. Now, the first thing is materials. Everywhere we heard the word material, and it is necessary to know about materials. Every engineer, it is not about physicists, it is not about material scientists. Every engineer like electrical, electronics, computer, mechanical, civil or other branches is concerned with the materials available to him. Whether the product is an electrical machine, an electronic device, a computer, a space vehicle, an automatic automobiles or bridge. He must have an intimate knowledge of the properties and behavior of the material and its characteristic or its property. In making his choice, the engineer must understand the basic of the materials. Now, man and materials have had a symbiotic relationship throughout the ages. Earlier, they have a very few materials to use, and depending on the materials, they designated civilization as a Stone Age, Bronze Age, Iron Age, etc. With time, man realized that heat treatment and addition of one material to another could change the property of materials. And with this knowledge, they discovered thousands of materials with specialized characteristics that meet the need of our modern society. The progress of human civilization is closely linked to the development in the materials. Nowadays, many scientists and researchers are investigating materials at a very small scale, and such a technological advance are known as a nanotechnology, and science which helps to grow this technology is called as a nanoscience. Now currently, nanotechnology is in infantile stage. It is the subject of much research and study, and as a result, it is developing rapidly. It has great potential for producing improvement and innovation in many areas of life. We shall now look at the materials that go into the nanotechnology products. Now, what material can be considered as a nanomaterial, right? That is the question. So, depending on the dimensions, we have a different type of materials: zero dimension nanostructure, one dimension nanostructure, two dimension nanostructure, and three dimension nanostructure. Now, if you consider the example of this sheet, now in this, the length and width might be greater than the nanometer, but the thickness of the thin film or you can sheet, that is in the nanoscale, right? Means two dimensions are greater than the nanometer range. Then here it is one dimension nanostructure. Now nanofibers, nanorod, nanowires, these are the nanostructures that is in the one dimension nanostructure, right? So this depending on this, we have a zero dimension, one dimension, two dimension, and three dimension nanostructure. Now we know that why we are interested to study the material in the nano range. One of the reason is that once the material size is reduced, the property get enhanced. Now what are the properties that can get changed? For example, the opaque substance may become transparent. The example is copper. Then stable materials turns into combustible materials. Example is aluminium. Then insulator become conductor, or example silicon, and solids turns to liquid at room temperature. For example, gold. Then nanomaterials have relatively large surface area compared to their volume. Quantum effect can begin to dominate the behavior of matter at the nanoscale, affecting the optical, electrical, and magnetic behavior of materials. Now, what do you mean by quantum effect? Now, the phenomena which can be explained using the quantum mechanics, which cannot be explained using the classical mechanics, that is the quantum effect. An example of quantum effect is tunneling phenomena, right? Tunneling phenomena is the quantum effect. Then the bulk property of material often change dramatically with nano ingredients. Means if you synthesis materials which have a nano materials or nano ingredients, then property also get changed in that case. Then electronic and optical property also get changed, because in bulk material, whatever the property we measured, that is the average property. And you know that earlier that we have categorized the materials into three. depending on the conductivity. For example, metal, insulator, and semiconductor. Now, metal, insulator, semiconductor are categorized depends on the band structure. We have a conduction band and the valence band. So in this, if you see the pictures of metal, then here the conduction band and the valence band are overlapped to each other. In semiconductor there is a small band gap. In insulator there is a large band gap. Now when we synthesize the nano materials in the nano range, then what happened, this band get discrete and we have a discrete energy levels. So the electrons in the bands are delocalized and no longer belong to a particular atom. One of the electronic quantity that is affected due to this change is a ionization potential. The ionization potential at small sizes is higher than the bulk work function and show marked fluctuation as a function of size. And if likewise, if you consider another properties, electronics, optical property that are also depends on the band structure. And when we reduce the material in the nano range, then your band structure is converted into a discrete energy levels, and because of that the property get changed. And that is what we are very much interested to synthesize the material in the nano range, and we get the improved or advanced property compared to bulk. Now next, now e-waste. Now you know that there is a lot of development in the electronic industry, and we have seen a lot of devices at our home. But one of the problem that globe is facing, that is the e-waste. Now the consumer electronics, IT communication technology, large household applications which is 42 and others. So considering all, that is 100% e-waste. So this e-waste considered as a hazardous waste due to its toxic ingredients like heavy metals and harmful chemicals. Mercury, sulfur, and lead are the major toxic contents in the e-waste. Now, according to the study of Center of Science and Environment, New Delhi, India, the volume of e-waste will reach nearly 0.7 million milliton by 2015 and 2 million milliton by 2025, as shown in the graph. So this issue can be solved by two ways, right? One way to solve e-waste toxicity would be to manage it properly, right? So e-waste management, right now there is a very less awareness in India considering this e-waste, because we know that the majority of all of us, we don't know how to destroy the battery which is present in our watch or electronic toys and all those things. We throw in the dustbin, right? So there is a less awareness. So if we are able to manage that e-waste, so that this problem can be solved. Another way is to replace the toxic material, whatever the toxic material we are using to fabricate these devices. So that material can be replaced by the non-poisonous or non-toxic materials, right? And that exhibit the comparable property. And this is the one of the motivation of my research work when I have done the work. So the first question in my mind was, what was the material I should choose? Then I came up with this literature, and I thought that I should work on the lead-free material, since lead is a poisonous and which is detrimental to the human health. Now, when I was doing literature, I observed that I studied that there are many lead based materials like lead titanium, lead zirconate titanate, lead magnesium nuboate, lead hafnate, lead standard zirconate. So there is a family of the lead materials. So why that has been used in the devices, which is used in the capacitor for and memory devices application? Because why? Because materials should have a high dielectric constant and lower loss for the application of a capacitor, and higher remnant polarizations along with the lower leakage current need for the application of FRAM. So for the application of sensor, actuator, transducer, materials should have a large piezoelectric coefficient, a rapid response, and an accurate displacement. The pyroelectricity has been employed in an infrared sensor because it can be operated at room temperature and meanwhile has good sensitivity and rapid response. But this family of ceramic materials contain lead, that is Pb, which is volatile and it is detrimental to human health and cause environmental pollution. So from the viewpoint of environmental protection on the earth and human health, The European Union in 2003 restricted the use of certain hazardous substances in electrical and electronic equipments, and therefore the efforts are being put to investigate lead-free materials exhibiting property comparable with the lead-based materials. Now, which material I should select, right? Then, when I have done the literature, I observed that the sodium bismuth titanate, its chemical. Acha. Oh, so you should inform me as early. There are many slides that I have shown. You could have informed me earlier. Sorry. Now it is visible, right? Now, why it is not changing? Now it is showing, but it is not the full screen. It should be full screen, na? Now, mm, what can be the solution for this? How should I share this? Yes. So what is the solution for this? Okay, just give me a minute. I will again rejoin the session.
Hello, am I audible now? Just let me share. Now it is visible. Now the slides are changing. Not changing. Only one slide is there. Okay. Oh, no, if animation should be there, na? Hmm, what can be the solution? Just a minute. No. After full screen, just a minute. Just a minute. Give me 5 minutes. Now it is visible, and now it is full screen, and now it is changing. Oh, ठीक है. So should I continue now? So we miss a lot of things. You should have informed me. That's the point only. Okay. So now I was discussing that man and materials had a symbiotic relationship throughout the ages. Earlier, they had a very few materials to use, and depending on the materials, they have designated as a steel age, stone age, bronze age, etc. And with the evolution of the materials, there is a development, human development that can be linked. So depending on the dimension of the materials, we have a zero dimension nanostructure, one dimension nanostructure, three dimension nanostructures, right? So now, what is the significance of this? I have already discussed this slide. So I have discussed why we are interested in the nanomaterials, because when we synthesize the nanomaterials in the materials in the nano range, because there is a drastic change in the property. And why there is a drastic change and what can be the properties? So any property that can be changed. For example, if you see the Opaque substance may become transparent in case of copper. Then stable materials turn into combustible materials, example of aluminium. Then insulators become conductor, example silicon, and solid turn to liquid at room temperature, example gold. Now, why this property take change? Because nanomaterials have a relatively large surface area compared to their volume. And you know that whatever happened in the nature that happened at the nanoscale. Now, the quantum effect can begin to dominate the behavior of matter at the nanoscale, affecting the optical, electrical, and magnetic behavior of materials. Now, what is the quantum effect? The effect or the phenomena which can be explained using the quantum mechanics, which cannot be explained using the classical mechanics, or that is called as a quantum effect. Now, example of this quantum effect is the tunneling effect. Then the bulk property of material often change dramatically with nano ingredients. So that is also you can get the better property. Then electronic and optical property. For example, in bulk materials, we have the band, that is conduction band, valence band. Now, if you see the metals, the valence band and conduction bands are overlap to each other. If you see the semiconductor, there is a small band gap in the conduction band and the valence band. And if that is the insulator, the band gap is more in the conduction and valence band. Now, when we synthesize the nano range, then what happened? This band structure convert into the discrete energy, and because of this, the electronical optical properties are changed. Now the slides is going well with my talk. Hello, am I audible? Ah, now the slides is going well with my talk. Okay, great. Now the slides number 4 is going on, right? This is in the corner, right? Right. Yes. So this was the slide we were discussing. Now you know that the electronic industry has been developed a lot, and there is a lot of coming up. So if you consider e-waste, e-waste called as a electronic waste. Now, if you consider the electronic instruments, so large household appliance consists 42%, then consumer electronics 40%, IT communication technology is 34%, and other 10%. So this much e-waste is low. Na, पूरी दुनिया is facing a lot this e-waste problem. And how we can manage this e-waste problem? If you see data which is generated by the Center for Science and Environment from New Delhi, the volume of e-waste will be go by 2 million milliton by 2025. And this issue can be solved by two way. One way to solve e-waste toxicity would be manage it properly, right? I was discussing we have a lot of battery at our home, but we don't know how to destroy it, how where we need to put it, right? We throw in a dustbin, और डस्टबिन से वो कचरा फिर बाहर गांव में जाता है, सिटी में जाता है, and it spoil complete environment, your water, your soil, your air, right? So if we have the awareness how to destroy the e-waste, then that problem can be solved. And another way to take care of this problem is to replace toxic material which we use in the devices fabrication or in the devices by the non-poisonous or non-toxic materials that exhibit the comparable property. And that is the exactly motivation of my research work. Then I have done the literature and I observed that the lead family is lead titanate, lead zirconate, lead magnesium, lead phosphate, lead stannate, zirconate. So there is a lead family which exhibits a very excellent property which can be utilized for the device fabrications. Majority of the time, these materials are used as in capacitors, and all the materials are categorized depending on the property like dielectric, ferroelectric, piezoelectric, and pyroelectric. Now, for the application of sensor, actuator, transducer, materials should have a large piezoelectric coefficient, a rapid response, and an accurate displacement. Now, pyroelectricity has been employed in an infrared sensor because it can be operated at room temperature and meanwhile has good sensitivity and rapid response. But this family ceramic material contains lead, that is Pb, which is volatile. So it is detrimental to human health and causes the environmental pollution. From the viewpoint of environmental protection on the earth and human health, European Union in 2003 restricted the restricted the use of certain hazardous substances in electrical and electronic equipment. Therefore, efforts are being put to investigate lead-free material exhibiting property comparable with the lead-based materials. Now, the next questions was which material I should study, right? So I observed that lead-free material, sodium bismuth titanate is one of the lead-free material which can replace lead-based materials. The chemical formula is Na0.5, Bi0.5, TiO3. Now, if you see the publications on sodium bismuth titanate in referred journal from 1980 to 2013, so there is a drastic increase in the number of research publications which is based on the sodium bismuth titanate. Then I thought this material is very good for the research purpose and it has an excellent property. Its Curie temperature is 320 degrees Celsius. Sintering temperature is 1100 degrees Celsius. Remnant polarization is 38 microcoulomb per centimeter square. Corrosive field is 73 kilovolt per centimeter. And piezoelectric coefficient is 79 picocoulomb per Newton. This material exhibits perovskite structure. So in perovskite structure, on the corner you have a sodium plus or bismuth 3 plus ions. Then in the body center you have a titanium 4 plus ions, and then at the fence center you have a oxygen O2 minus ions. So depending on the range, this material exhibits in the rhomboidal, tetragonal and cubic structural phase. Now when I observed, there is a vast investigation in bulk and there are very few literature or research paper they mention the thin film of this material. So this thin film has been deposited, thin films of sodium bismuth titanate have been deposited using radio frequency magnetron sputtering, sol gel process, sol gel spin coating, chemical solution decomposition, and pulse laser deposition technique. So that time there is a only one research group in 2008 who published the research paper of sodium bismuth titanate thin film using pulse laser deposition techniques. Now I had a lot of questions in my mind. Can we improve the property of NBT thin films using pulse laser deposition technique? Is there any optimization strategy other than trial and error method? How this methodology and strategy will help me to improve the property? And the answer of these questions become the problem statement of my PhD thesis. And the main purpose of my PhD is to grow good quality single phase NBT thin films using pulse laser deposition technique and study the structural surface morphology and electrical property at room temperature. Then so this is the schematic of the pulse laser deposition techniques where this is the laser, ARF laser. This is the vacuum chamber. These four dots represent the target. Target means it is the palette of the material of which you want to deposit the thin films. And this is the substrate holder come heater. Now when high energy laser incident on a material, the material get evaporated and evaporated material deposited on your substrate. Now, the thin films can be deposited by various type of materials like sputtering, molecular beam epitaxy, metal organic chemical vapor deposition, metal organic molecular beam epitaxy, and sol gel methods. Among these methods, the pulse laser deposition techniques have a lot of advantage. So, what are those advantages? It is a very good control over film composition stoichiometry. Wide variety of gases or gas pressure and temperature can be utilized to deposit the films. Then microstructure can be independently varied by employing the different thermal cycles. The deposition process is very clean and is mostly confined to a very small area near the substrate, thus eliminating the chances of contamination. And this process does not involve the bombardment effects of thin film or plasma species as in the sputtering. Right? Because of this advantage, I choose to select this method to synthesize the thin film. Now, after successfully synthesizing the thin films, I have studied the surface morphology. So you can see this is the scanning electron micrograph in which you can see there is a substrate platinum coated silicon that is platinum is 100 nanometer, and this platinum coated silicon substrate you can get ready-made in the market, on which I have deposited the thin films of sodium bismuth titanate, which is a 400 nanometer. This is the cross-section view, and this is the top view, where you can see the different type of grain and grain size. And because of this surface morphology, the property, the dielectric property of the thin films are depends on the microstructure. That is what the study of microstructure in the nanoscience and nanotechnology is very important. After optimizing all the parameters like pulses, depositions, and compositions, all the parameters of the chemically and the instrument, we have successfully deposited the thin films which have the excellent surface morphology or microstructure. After that, since we are looking for this uh, dielectric capacitor applications, so it is very much important to study the dielectric constant, dielectric loss, P loop, polarizations loop, then the fatigue data. So this is the data from the very ideal optimized sample, sodium bismuth titanate, which is on the different substrate, right? And few research paper has been published during my PhD on this work. Then what is next? इसके बाद क्या होगा? That was the question. What is next? And then I thought that now I have deposited the thin film of sodium bismuth titanate, right, which is a two-dimensional nanostructure. Now, can we synthesize the one dimension, right? So, when one-dimensional nanostructure, you know that that is the nanofiber, the nanowire, right? So, one-dimensional nanostructures such as nanowire, nanotubes, nanoribbons, and nanofibers are continuing to be at the forefront of nanoscience and nanotechnology. Several ferroelectric and piezoelectric nanowires and nanofibers are promising in making great breakthrough. Right? So nanofibers belong to the class of nanomaterials with diameter less than 100 nanometer and aspect ratio is greater than 1000 and are characterized by high surface area to volume ratio. So it is a potential candidate for large number of applications because of the combination of high surface area to volume ratio and structural flexibility. Because every nowadays flexi electronic research is going on, and every device we want flexible. So the huge surface area available on the nanofiber makes it very suitable for our new technology, which requires smaller and smaller environments for chemical reactions to occur. So increasing the surface with a chemical reaction. Now, nanofibers are pure and no NB26 material for sensing and actuation is still an essential that drive the development of piezoelectric ceramic fiber. This leads to the origin of this project, that is electrospinning of lead-free NB26 based material for sensor and energy harvesting applications. So when I have done the literature, then I thought that there is a lot of number of research paper number of increasing in case of study of the nanofibers, and these are the advantages. Why nanofiber? Because it is because of the large surface area to volume ratio, high porosity, high mechanical strength, high thermal and chemical stability, high corrosion resistance, flexibility in functionalizations, and the biocompatibility. Because of these advantages, uh, the nanofibers, one of the nanofibers of the any kind of materials are very much important. And then I wrote the research proposal for the DST when I joined as an assistant professor in IIT Nagpur. And luckily, you can see this project has been approved by the SERB DST. So the title of the project is Electrospinning of Lead-Free NBT-BT6 bed material for sensor and energy harvesting applications. Now the question is, why electrospinning? There are many methods by which we can synthesize the nanofiber. Few of them template synthesis techniques, phase separation techniques, self-assembly techniques, and the electrospinning technique. Now, why it is electrospinning techniques? I choose it has the ability to produce continuous nanofiber of different polymers and capability to generate ultra thin fiber of calculable diameter, composition, orientation, and high entrapment efficiency, control over pore geometry, high surface area, and high encapsulation molecules. So these are the advantage of electrospinning technique, and that is what I have choose the electrospinning techniques to synthesis. Now, in recent years, numerous electronic devices have been developed, including devices that can be worn on the body, such as smartwatches, fitness tracker, and even smart fabric. As the demand for these wearable devices has grown, power issues have become a major consideration. In general, wearable devices with battery must be lightweight, flexible, stretchable, and highly durable. So most importantly, the battery should be able to self-generate so that wearable devices can operate without having to be charged externally. And most wearable devices generally use power stored in the form of electrochemical energy in the battery. However, it is not only difficult to make a flexible battery, but also the battery must be replaced or recharged. And some researchers attempt to meet this challenge by proposing a self-charging battery that harvests the energy from various sources such as solar energy, electromagnetic energy, and the wind energy. So batteries charged with such a source are often unstable because they are affected by the surrounding environment as they charge. Whereas energy harvesting from body movements have the advantage of being less affected by the surrounding environment. Right? You know that we can convert one energy into another energy. Right? And for flexi electronic devices or the wearable devices, if we are able to convert the energy or generate the energy from the body movements, so that will be the great things. So there is a one material which can convert mechanical energy into electrical energy, and I hope that you all know, right? That is a piezoelectric material. So piezoelectric materials, when we apply the mechanical force, so that materials can generate the electrical energy. So piezoelectric energy harvesting is providing to be one of the best methods to harvest energy from the human body movements. There are various piezoelectric ceramic forms such as bulk, nanomers, and nanofibers. The bulk form of piezoelectric ceramic has excellent characteristics, no flexibility, right? Then, on the other hand, nanomers have a good flexibility but are difficult to produce in large quantity. In addition, it is difficult to manufacture them using various materials owing to the limited materials that can be manufactured. Piezoelectric nanofibers have advantage when used as an energy harvester in wearable devices due to their simple manufacturing process with good applicability to polymers and the piezoelectric ceramics. Now, electrospinning techniques. So we will see little bit brief about electrospinning techniques. Just give me a minute. Now, everything fine, Dr. Korde? Okay. Okay. So, electrospinning technique. So electrospinning is the most widely and successful technique used for fabrication of nanofiber. Now a schematic diagram of this electrospinning technique is shown on the slide. So this demonstrates the process of electrospinning of polymeric nanofiber. So there are fundamentally three components. They are as follows. One is high voltage supply. If you see the power supply cable, so through which we can provide the high voltage, which is from 1 kilovolt to 50 kilovolt. Then capillary tube with pipette or needle of small diameter. So this is like a syringe. ना जो हमारा इंजेक्शन होता है ना वो syringe है. ठीक है. So this is the needle. Syringe with needle. So there is also infusion pump. So this pump automatically pump this syringe, and then the solution will come outside of this needle. Then the third is that a metal collecting spin rotating cylinder. So if you see this part, so this is the collector. This cylinder is known as the calendar collector, right? So in this technique, a high voltage potential is connected to a syringe which produce an intense electronegativity charge jet of polymer solution. The needle of syringe act as one of the electrode and the collector act as the second electrode, which is located at a small distance of 5 to 25 centimeters. Again, you have to optimize the parameter distance between collected to needle. It may be vary for different material. Now, an electric field is applied across the tip of the needle, ranging from 1 to 50 kilovolt, which makes an electronegative drop molecule. The surface of the drop becomes hemispherical and starts getting stretched in the form of cone-like shape after reaching the applied field. Now, at this critical point, the applied electric field eventually becomes more prominent and overcome the surface tension of the liquid, leading to the charged jet of the solution ejected from the tip of the Taylor cone. Now, if you see this spiral like this, so this brown color is the Taylor cone, and this is the far field, means this is the spiral jet. Now, as the jet travels through the air with an unstable whipping of the jet occurs in the space between the tip and the collector, this leads to evaporation of the solvent and leaving behind the solid continuous one-dimensional nanofiber deposited over the grounded collector. Right now, this phenomena is similar. You might have observed your grandmother or mother fabricating the fiber of the cotton. So what they do, they they keep the bundle of cotton in one hand, right, and by other hand they just extract that cotton by applying the mechanical force in a proper direction in proper rotation, right, and you can synthesize the cotton fiber from that cotton. In this case, the mechanical force is playing an important role. But in electrospinning, the electric field between this needle and this collector will play the important role. And because of the force of electric field between two electrode, there is a synthesis of fiber. Because of that, the solution get charged and that is extracted in the case in the form of spiral jet and collected on the collector in the form of nanofiber. I hope you all understood the uh, phenomena of electrospinning. If you have any doubt, we can consider for the discussion. Yes. Now, the target was to synthesize the nanofiber of sodium bismuth titanate, barium titanate compositions, NBT-BT6. So we have follow this method to synthesize the solution of the polymer-based solution of the sodium bismuth titanate, and we have optimized the parameter. So applied voltage is 21 kilovolt. Solution flow rate was 0.4 microliter per second. Distance between collector and spinner's is 15 centimeter. Nozzle diameter is 24 gauge and the plastic syringe of inner diameter is 13.8 mm. These are the parameters for the synthesis of the nanofiber. But it is not so easy. You have to optimize all the parameters to synthesize the nanofiber successfully. Now, apart from this instrument parameter, you have the solution parameters also, right? So these are the parameters which will affect the quality of the fiber or which will decide that fiber will be synthesis or not. If you see the solution parameter, there is a concentration, molecular weight of polymer, viscosity, conductivity, and the surface tension. You need to take care of all the parameters while synthesizing the solution for the nanofiber. Then processing parameters, applied voltage, distance between collector and needles, flow rate, and the needle diameter. And the ambient parameters like temperature and humidity also affect the process of the nanofiber. Now, if you see the parameters, solution parameters like polymer concentration, molecular weight of a polymer, conductivity, viscosity, surface tension, solvent volatility, solution temperature. So, see, the polymer concentration significantly affects the fiber size, its morphology, chain entanglement, and uniformity of prepared nanofibers. Polymer concentration also play a decisive role on the outcome of the electrospinning process. Low concentration lead to the formation of bedded fibers and intermediate concentration yielded good quality fibers. A high concentration result in the biomodel size distributions and at even higher concentration distributed depositions. So depending on the polymer concentrations, we can get the different kind of fibers. Then highly conductive solutions will form greater charge carrying capacity and higher tensile strength fiber. The solution of zero conductivity cannot be electrospoon because your solution should be conducting, because it will work in the it should be extracted from one electrode and should be collected on the another electrode. So if your solution is not conducting, that is zero conducting, in that case we cannot spoon the fiber of the material. So your solution should be conducting. Then solvent volatility mainly affects the fiber fabrication techniques, morphology, and the fiber porosity. High voltage solvent should be used. Volatile solvent should be used to prevent incomplete fiber drying. Right, when the solution get extracted from the needle, so that solution should get evaporate and you can get the fibers on the collector. If the solvent is less volatile, then what will happen? The flat ribbon-like nanofiber is derived. A phase separation occurs while fiber jet journey over atmosphere to the collector, a process greatly influenced by solvent volatility. The solvent volatility also affects the kinetic of phase separation and the fiber morphology obtained and electrospinning. So overall, if you consider the polymer concentration, conductivity of the solutions, volatility of the solutions, and polymer concentration play a very important role to get the desired fiber. Another thing is applied voltage. Now we have to apply the electric field or a high voltage in between two electrode. One electrode is your needle, other electrode is your collector. So in between you have to apply the high voltage so that your solution will get extracted from the needle and collected got a fiber from the collector. Now, high applied voltage will increase the instability and stretching of the jet and produce smaller fiber diameter if we use the high voltage. Now, size range of nanofibers can be controlled by controlling the strength of the applied voltage to an optimal value, which is different from different polymer. Right now, the polarity of the tips. The capillary tip polarity mainly affects nanofiber quality, dimension, diameter, and the areal density. The negatively charged capillary tips produce average diameter, which were found to be significantly larger at all concentrations. A capillary tip of negative polarity decrease areal density of a fiber mat spoon due to increased number of charge per unit jet segment. So the polarity of the electrode is also very important. Then feed rate. The feed rate of the polymer solution mainly controls the nanofiber size, shape, moisture, content, porosity, and release of the encapsulated drugs. The fiber diameter and pore size are directly proportional to the flow rate. Lower and the higher feed rates cause Taylor cone depletion and large fiber diameter respectively. So the dimension of the fiber, that is diameter of the fiber, can be optimized or can be controlled by the feed rate, polarity of the tips, and the applied voltage. Then collector geometry. So in the picture, I have shown you the simple collector, that is a cylinder, right? So in laboratory electrospinning, an immobile metal plate or a foil is positioned at a fixed distance from the tip. Grounded collector rapidly remove the remaining charges on the assumed spoon fibers, permitting the fibers to merge into high areal density mat. Now we have a different kind of collector depending on the application, depending on the requirement of the nanofiber. What are the nanofiber you would like to have for the particular application? You need to use the particular collector. Now you have a, cylindrical collector, plain cylinder. It can be used as a collector. You have a plain, uh, what you can say, immobile metal plate that can be used as a collector, right? You have a cylindrical collector which have a bar, लाइक हम पतंग उड़ाते हैं कि टाइम में जो चक्री हम यूज करते हैं, उस तरह का भी मेटल कलेक्टर वी कैन यूज टू सिंथेसिस द नैनो फाइबर. Then collector material. The grounded collector surface will cause the exclusion of electrical charge on the fibers. The removal of charge from first nanofiber layer rapidly and in subsequent layer will be slower. A non-conducting or conducting ungrounded auxiliary collector surface mainly affect the packing density or the solidity nanofibers which are interpolated between the tip and the grounded plates. So the material of the collector is also affected, the quality of the nanofiber. Then needle tip design and placement. So needle tip design and its placement play a critical role in fabrication of composite, hollow and parallel nanofibers. A lot of designs and configuration of needle tips such as metal, glass or plastic have been investigated for electrospinning process. A capillary tip movement through the length of the drum collector produces smooth nanofiber. So you can synthesize the single nanofiber or you can synthesis the कोर नैनोफाइबर. कोर नैनोफाइबर मतलब अंदर एक इनसाइड वन मटेरियल होगा और उसके ऊपर दूसरा मटेरियल होगा. जैसे हमारा केबल होता है, तो वायर में क्या होता है, तो कॉपर और एल्यूमिनियम का एक वायर होता है और उसके ऊपर प्लास्टिक का पॉलीमर का कोटिंग होता है. उसी तरह कोर नैनोफाइबर वी कैन सिंथेसिस यूजिंग दिस इलेक्ट्रोस्पिनिंग टेक्निक. Then the distance between needle to collector, that is called as a TCD, tip to collector distance. That determine the time for the solvent to evaporate before the nanofiber reach the collector surface and mainly depends on the property of the solvent volatile. The voltage gradient, spinning cycle, and the polymer stretching during the spinning process, which in turn affect the moisture content, porosity, and the size of the final product. Decrease in TCD mainly affect the fiber surface morphology and the average diameter. The quality of the nanofiber mat gradually decline as the lower TCD, right? अगर the distance between needle and collector should be optimum. अगर बहुत कम होता है तो क्या होगा? So the whatever the solvent is there in the solutions that cannot be evaporate, right? और ज्यादा होगा तो क्या होगा? It is very much difficult to collect the solution in the form of nanofiber on the collector. So ज्यादा भी नहीं चाहिए और कम भी नहीं चाहिए. We have to optimum that parameter to get the desired good quality nanofiber on the collector. Then nozzle diameter. So an increase in the nozzle diameter eventually increase the fiber diameters, distributions and productivity. This can be due to the higher mass being available for the electrospinning techniques. Then environment, obvious. Any chemical reaction for any experiment, the environmental parameters are very much important. So the electrospinning process and the physical characteristic of the fibers are affected by the temperature and the humidity of the environment and due to its effect on the rate of evaporation of the solvent and solution sensitivity to humidity. So considering all these parameters, we are able to successfully synthesis the nanofiber of the sodium bismuth titanate, barium titanate compositions. So on this slide, you can see the scanning electron micrograph of the fiber at a different resolution. So now this is the distributions of the nanofibers. There's how many, what are the nanofibers, what is the diameter, right? So if you see, so there is a 1 to 200 nanometer red color, 28.57% are nanofibers are there, which is in the range of 1 to 200 nanometer. Then 42.86 percentage nanofiber, which is in the range of 200 to 400 nanometers, right? Then 400 to 600 nanometers, and then 600 to 800 nanometers. That is the diameter of the nanofiber. So the highest diameter of the nanofiber is 800 nanometers, and the minimum diameter of the fiber is 1 nanometers. So there is a different kind of this electroscanning techniques. Then what are the application of this nanofiber, right? So this nanofiber can be used in the three tier concept to fabricate high flux and low fouling ultra filtration membranes. So in filtration industry, these nanofibers are very much important. Then the fuel cell, that is micro nano electrode devices. In fuel cell you can use the nanofiber. Then you can use this nanofiber in drugs delivery, scaffold or tissue engineering, wound dressing, biosensors, and medical implants. Now, based on the literature survey and current achievements in the electroscreening, electrospoon nanofibers are expected to play an important role in various applications area. Now, you can see that can be used in the cosmetic skin mask, skin cleaning, skin healing, skin therapy, filter media, liquid filtration, gas filtration, molecule filtration, nano sensor, thermal sensor, piezoelectric sensor, biochemical sensor, fluorescent and optical chemical sensor, right? Then other electronic applications like micro nano electronic device, electronic dissipation, electromagnetic interference, photovoltaic device, LCD, ultra lightweight spacecraft material, high efficiency and functional catalysis. On this side, you can see the military and the medical applications where nanofiber can be used. Now, improved large-scale nanofiber production is offer high-quality nanofibers and reduce the application of cost. According to the emerging trend, new discovery and patent promise nanofibers in upcoming years. Now, one of the applications that we are going to discuss, that is the energy harvesting applications. So, wearable core cell piezoelectric nanofibers ANS for body movement energy harvesting applications. Now, this is the paper published by Sang Hoon that I have considered for the discussion. Now, in this paper, they fabricate a variable piezoelectric energy harvester based on core cell piezoelectric ants with external electrodes. So, flexible piezoelectric nanofibers of BNTST, right? BNTST. So, this is the chemical formula. So, it is also the composite material of sodium bismuth titanate and the ST, that is strontium titanate. So, it is short form is BNTST. So, and so they have fabricated the core cell piezoelectric lamps with external electrode and flexible piezoelectric nanofibers of these BNTST materials and the polyphenylidene fluoride trifluoroethylene polymer were initially electrospin. Then subsequently, the core cell piezoelectric nanofiber and were prepared by twinning the ends around the conductive thread. So to create the outer electrode layer, the core cell piezoelectric nanofiber and were braided with conducting thread. Then core cell piezoelectric nanofiber and with external electrode were then directly stitches onto the fabric. Let me show you a diagram here. So now see, this is the conducting thread. This is the inner electrode. On what? There is a BNT ST nanofiber mat has been rotated on this conducting electrode. Then core cell piezoelectric nanofibers, core cell. So see, this is the figure in which there is a core cell. This is the conducting thread and this is the piezoelectric nanofibers. So this is the core structure nanofiber. With external electrode were then directly stitched onto the fabric. So this has been stitched into the fabric. So if you see, there is a core cell structure piezoelectric and this shown in the yellow color, and there is a red color fiber that is the conductive thread. So that has been done. So in bending test, the output voltage were investigated according to the total length, area, and stitching interval of the piezoelectric cans. The stitching patterns of the piezoelectric cans on the fabric were optimized. Based on this result, the output voltage of the stitches piezoelectric cans on the fabric were improved with an increase in the pressure and the output voltage characteristic were investigated according to the various body movements, especially in the pressing conditions. So you might have understood that how they have synthesized this core structure nanofiber. In this core structure nanofiber, there is a there is a conducting thread, and this is the piezoelectric nanofiber, right? And this is the scanning electron micrograph where you can see the nanofiber. This is the fabric, and this is the in yellow color you have a core cell structure piezoelectric and this is in the red color. This is the conductive thread. In this way, they have the fabric in this core cell piezoelectric ants with external electrode. Now, since these nanofibers are synthesis from the piezoelectric material, and piezoelectric material has the property to generate the electricity or generate the convert the mechanical energy into the electrical energy. Now, to study that, they have measured the voltage and the voltage, output voltage according to the total length, then effective area, and the stitching interval of core cell piezoelectric cans during the bending test. So during bending test, so this is the first diagram represent the voltage and the total length. So the total length of the fiber is 5 centimeter, 10 centimeter, and the 15 centimeter. For this length and this on x-axis, you have a time that is it is in the second form, right? So if you see for length 5 centimeter, so there is a generation of the voltage which is greater than 0, like around 1 volt, right? If you see here in the second diagram, there is a module width 5 centimeter length and 50 centimeter, then module width 3 centimeter length and 9 centimeter, then module length 3 centimeter length and 15 centimeters. So this is the effective area. So this is the effective area. So now for this effective area, you can see there is a generation of voltage from 5 to -5 millivolt, right? And now here there is a interval 0.5 centimeter, 0.3 centimeter, 0.15 centimeters. So they have changed the interval of this fiber, the distance between this fiber by forming different kind of shape on the fabric, and they have studied the voltage generated from the bending test. In other characterization, they have used that they apply the pressure on the fabric and then measure the generated voltage. For this, they have a special instrument which is shown in the figure. So equipment used to apply the constant pressure to a piezoelectric energy harvester module stitched with a width of 0.7 centimeters and the interval of 0.15 centimeter by the core cell piezoelectric cans and output voltage according to the applied pressure. If you see the diagram here, so on x-axis there is a pressure in kilopascal and there is a generated voltage which is in the volt. So when you increase the pressure from 10 kilopascal to 50 kilopascal, so the voltage generated voltage is increasing, right? So after that, at the extreme pressure, there is a decrease in the voltage, or you can say zero. So again you can get the voltage from in the particular pressure. So also you have to optimize the pressure for these two characterizations. Then they also study this sample. So this is the A figure. This is the figure where there is output voltage, output current, and output power according to in the bending and the outbending fingers moment as a cotton glove stitch in the finger parts with the core cell piezoelectric can is worn, and output voltage, output currents, and output power according to bending and the output bending has been studied, right? So they have studied this fabric on the fingers, in the palm, and on the bending of the elbow, right? So and they have synthesis, they have prepared this special fabricate with that sample, right? So see, there is a signal of the voltage, current, and power. Here it is in the B, it is from the elbow bending test, and it is from the knee bending test. So on the body part, they have done this calculation at three places. One, on the palm, where you have a bending fingers, on elbow, and on the knee. So for this, they have special fabric. On that fabric, they have put they own the our sample, that piezoelectric nanofibers with the core structure, and they study the the how that mechanical energy, that is the moment of the body, is converted into the electrical energy. Then again, they have studied the clapping moment. So output voltage, then output current, and the output power according to the clapping moment as cotton glow stitch in the effective area with the core cell piezoelectric ends to on, and output voltage, output currents, and output powers according to the walking and running moments as a shoe insole stitches in the effective area with the core cell piezoelectric and is born. For this, they have to prepare special type of assembly to do study that how the body movements, how the mechanical energy will convert into the electrical energy, or how many pressure, or how many bending that voltage can be generated. So that is the complete study that has done by that group, and in this way we can synthesize the nanofiber of lead-free materials, piezoelectric materials for the energy harvesting application. So I conclude my talk here. So let me summarize the talk. So today we have discussed why lead-free materials are very important for the electronic devices to avoid the problem of e-waste or to reduce the problem of e-waste. Then we have discussed how we can synthesize the nanofiber using electrospinning techniques, in which I have discussed the process phenomena of the electrospinning techniques. Then the parameters of the electron spinning techniques and the effect of that parameters on the quality of the nanofibers, how we have to optimize that parameters to get the good quality nanofibers, and then application of the nanofiber. And in application of the nanofiber, you might have learned that the nanofibers can be utilized in the military applications, electronic devices, in medical field, right? And the energy harvesting application is one of the uh, excellent applications of this nanofiber, piezoelectric ceramic nanofiber. So many of the contents such as text, figures, image, photos, audio, and video in the PPT has been taken as it is from various books, research papers, and website. This information has been used for academic purpose and not for commercial. So I would like to acknowledge and thank all the anonymous authors, co-authors, designers, and photographers, and all for the information which I have taken from the various sources. So I would like to thank you, the organizing team and the coordinating team of the KJ College of Engineering and Management Research, Pune. So thank you very much. And now I will request all the participant, and I will also request coordinator to unmute participant for the discussions. Thank you very much. Yeah, you can write in the chat box because now I can access the chat box also, or you can unmute yourself and ask the questions. Yes. So Dr. Ompal Singh, thank you very much for encouragement. I think all the participant in the talk might be a master or graduate, or doctor and faculty. So you can ask me the questions, and also you can visit the website. Let me share the one website too with you. Yeah, already shared. Okay, so um, Vijay Rahangade, thank you very much. I have shared my link, Triple IT Nagpur website, where you can see my profile, my contact number, my email address. You can approach. And second link I would like to share about my lab. my research lab, where you can see all the facility that I have with me. And if you would like to do research in this field, so you can don't hesitate to contact me for the same. So I have shared both the link. Thank you, Aruna Macharkar. Thank you very much for your feedback. So I have shared both the link. You can save that link for in future if you would like to contact with me. And those who are master degree students, they can also apply for the internship. They come to Triple IT Nagpur. They spend here 6 months of 1 year and do internship with under my guidance. Is there any question? Thank you, Pavar. Thank you very much. So more or less, I have keep this as a little bit high standard by considering the audience. So Dr. Korde told me there are many faculty will be in the session. So I just consider the content which is the research base, and know that with the help of that you can do the research. We can pursue the PhD. You can identify the problem in this field. Thank you, Dr. Ompal. Thank you all. Is there any doubt, questions regarding topic or regarding sessions or anything that you would like to share? Dr. Ompal, where are you from? Can we unmute Dr. Ompal, Vivek, Dr. Korde? Can we unmute the participant? Can they unmute themselves?
Sir, hello, sir.
Yes, Dr. Ompal. Where are you
I
from?
belong to Agra, sir.
Agra. And you
Yes.
are working as an assistant professor?
S. Chandra Mahila Mahavidyalaya, ASTI, affiliated to Gondwana University, Gadchiroli, sir.
Acha, Gadchiroli. And what was your PhD topic?
PhD topic floristic studies on the dwindling vegetation from district Hathras, UP, with a special reference to their medicinal uses, sir.
Okay, so now you can go in the nanoscience and nanotechnology also. You can
Yeah,
extend your research work. You can write some research proposal.
my colleague is Dr. N. Padole, sir.
Mhm.
This work is very nice and nanoparticles in physics, sir.
Right.
Yes, sir.
Right.
So I am
Thank
very,
you very
very
much.
interested for the nanoparticles, sir.
Okay, great.
Yes,
So now you can synthesis the nanoparticle using solid state synthesis method or sol gel synthesis method
the
or
work,
hydrothermal method.
my work is, sir, only medicinal use purpose, sir.
Right, biomedical field.
Yes, yes, yes.
Great.
Yes.
So if you
Thank
need
you
any help in
very much.
future, you can contact me.
Your very nice presentation, sir.
Thank you very much.
Okay, thank you.
Thank you. Asha Pawar. Asha Pawar, can you unmute yourself?
Yes, sir.
Where are you from, ma'am?
Sir, I am from Nasik.
Acha. And what is your qualification? PhD?
Sir, I am pursuing PhD. Uh,
What is the topic?
sir, solution chemistry.
Acha, solution chemistry. Your background is chemistry?
Yes, sir. Yes, sir.
Okay, great. So
Thank you.
because what happened the research now whatever the research is going on, that is a multidisciplinary research. So
Yes,
now
sir.
physicists, chemists, doctors, engineers should come at one platform and share their knowledge, so that then we can have a interdisciplinary research. So whenever you write the research proposal to the funding agency, you just try to have the collaborator, right? If you have a more collaborator in your research proposal, if, from the diverse area, and if you have more institute in your research proposal, then the possibility to accept that research proposal will be more. So always just consider this point for future.
Yes, sir. Thank you. Thank you, sir. Session is very nice, sir.
Thank you very much. Yeah, please. Right. Yet. Y- Yes, yes, you can synthesis. But would you like to have a composite of that material or separate? Ah, yes, yes. Right. So one point need to be considered, Dr. Korde, here. When you say the nanomaterials, no, nanomaterials can be formed in the form of powder, right? Nanomaterials can be synthesis in the form of thin films. Nanomaterial can be synthesis in the form of nanofiber or nanowire, right? So depending on the facility available, you can choose the approach, right? So to synthesis the materials in the form of powder is very sophisticated or very easy to synthesis because it won't require the high cost facility. If you are thinking for the nanofiber, then you have the electro spinning setup which is cost around 15 lakh rupees, 15 lakh rupees, right? So if you want to synthesis the nanofiber, then my lab has this facility, or otherwise in Pune might be there are many groups which can have that facility, right? So first of all, synthesis any kind of research, first of all synthesis that material in the pure powder form, and then think about the thin films and the one dimension nanostructure that is in the fiber form. Okay. Yes. So actually, when we see the materials, then depending on the structure, we have a three kind of materials. One is amorphous nature, in which we don't have a order. Then we have a polycrystalline material. Now, polycrystalline material consists of grain and grain boundary, right? And what is grain? Grain is the small portion of the material, right? And grain boundaries are the boundary which are separate the grains, right? And in single crystal, we have a full range order, right? When you see the single crystal, there is, yes, there is no grain boundary. There is only one domain you can consider for the single crystal, right? But when you synthesis the polycrystalline material, so in that there is a domain. Now, what is mean by domain? Domain is nothing but the small area in which you have the order range, right? So अगर उसमें yes order structure. So एक डोमेन में एक तरह का स्ट्रक्चर हो सकता है कि दूसरे डोमेन में दूसरे तरह का स्ट्रक्चर होता है, right? So now there are a dipole, right? So in particular domain, the dipoles are oriented in one direction. So when we apply the external field, what happened? All the dipole will be aligned in the electric field, one direction, and then you can say that that materials are polarized, fully polarized, right? Now the polarization and depolarization depend on the dimension of the domain. If you have a more domain, then it will be very difficult to polarize that material, right? So you want large domain, and that large domain can be synthesis by optimizing the particular parameter for the particular method. For example, if you are synthesizing the thin film of that particular metal using PLD, so then by changing the parameter you can see the surface morphology, you can see the domain and domain structure, grains and grain boundary, and then you can study your desired property, and then you can conclude if this sample is very good because the domain size is greater compared to the other sample. In this way, yeah, single crystal means single domain only, right? Yes 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 Is there any? Yeah, is there anyone? Because I encourage all the participant to interact. If you have a little doubt or if you want to share anything, you can share your PhD topic, your research work, where you are stuck or you have any problem in your research work. That also you can discuss. I will try to help you out. There is a in chat box. There is a Sudhir Taksale. Is he there? Yes, Sudhir. Where are you from? Sachin Kulkarni is there. So those participants who are pursuing the PhD, they can share with me their experience. Okay, I think all participants are satisfied. So thank you very much for patience and participating in this online STTP. So it's always a great pleasure to interact with the young faculty and students. But I encourage organizer to organize such a activity in offline mode and invite us in your campus so that we can visit you personally. So thank you very much, Dr. Korde. Okay, would you like to take a few photo so that we request the participant to switch on their camera if possible and we can take a photo. You can take a screenshot. I request participant to switch on their camera if it is possible. Vivek, have you taken? Done. Okay. Thank you. Should I leave the now? Okay. Thank you. Thank you very much. Thank you very much. Yeah, that is there. I have shared the link. Or you can note down. I will tell you. 98. Uh, okay, I will just type in the 9867245331. I posted in the WhatsApp. Sorry, in the chat box. 9867245331. So thank you very much, all of you. Thank you. Should I leave? Okay.